Hello. Today we're going to be looking at the Rachford-Rice equation, and specifically how to do a flash drum calculation at a constant pressure and temperature, and also at a constant feed and feed composition. So this video is going to be hot off the presses of the other one. You can see those beautiful graphs we did right here. So we're just going to begin by typing in the parameters of this simulation. So we're going to assume, just like before, our pressure and temperature are the same, but I'll rewrite them just to keep those numbers fresh and where we need to see them. So the temperature we're going to be working at is 393 Kelvin, and the pressure is going to be 150, I'll do it the fancy way, E3 this time, instead of just typing out the extra 3 E's, because we save an extra keystroke. So there's our temperature and pressure of our flash drum. So now the other thing we need to worry about is the feed and the feed composition. So the feed is going to be simply 10 moles per second. I'll just say moles per sec feed. And then our composition, Zi, so the feed fraction of each component is going to be np dot array. Then in here it is going to be 0.4 benzene and 0.6 toluene. So that's going to be our composition. So those are all of the given parameters we have. Now, using some of the derivations we figured out in the previous video, or video 3, despite all those technical difficulties, it did get filmed in one piece, but not recorded in one piece because of my phone. So I'll pull that up right about now so we can see the last 3 pieces we're going to need. Obviously, is going to be the Ki, the substitution of Xi, which we don't know, for things we do know except for V over F, and then how that all cleans up to look as our final Rachford-Rice equation right there on the right that's equal to 0. So the thing we're going to need, obviously, is Ki, since we use that in the formula. So we're going to define Ki right here, not I caps lock, Ki. Well, Ki is, again, equal to Yi over Xi, but we don't know either of those. So instead, we can substitute them to be the pressure of vaporization versus divided by the pressure of the system, which we know that, and we can figure out the pressure because we know the temperature. So that's going to be P dot evap of P divided by P, capital P. And that's all we have to worry about because that's our Ki taken care of. The next thing we're going to do is actually we're just going to use the Rachford-Rice equation that we derived in the previous video, and we're just going to define it as a function that can be root solved for our V of F, because again, it's like previously where it's analogous to before when we had the pressure that we wanted to get but didn't know the temperature we needed to get there. It's similar where we know it's equal to 0, but we know the feed and the feed composition we have. And all we want to do is basically get this equation to be equal to 0. So we don't actually have to subtract it from anything. We can just type in the Rachford-Rice equation as written. So we're going to define this as RR. I should probably hit save define. Define Rachford-Rice. And of course, since we're going to be putting it into the root solver, we're going to need it to be a vector. So we're going to need to unpack that vector. So what's the only thing we need for the Rachford-Rice? Well, all we need is the Zi, I believe. So we're going to say Zi is equal to vec 0. Oh no, because this is the thing we're solving for. The one thing we actually need is the Zi, but again, anything that's not defined in this function that we're not pulling in will be just gotten from the code source of it. But the thing we're actually, obviously, the thing we're looking for in the root solver to solve is the V over F, that fraction, the vapor fraction. Again, there's an arrow pointing right at it. It says vapor fraction in that chalkboard video. So we need to have V over F, so V over F here. This is what we're going to be solving for, so that's what we want to pull in as our vector. So then we just need to generate return the Rachford-Rice equation in terms of V over F, which again is going to be iteratively whittled down to the correct answer. Pardon me. So what do we need to be equal to 0? Well, we need it to be Zi divided by the sum, so np dot sum. And what's the sum going to be of? Well, we need the sum to be of each of the V of F, so it's going to be V over F plus, because V over F, again, is a constant, so that's going to be, added together as many times as we need. That's why we're solving for it, is because it's feed specific. It's not specific to any of the components. And then each of the component parts, which is just going to be 1 divided by, I'll put it together. So 1 divided by, and then parentheses, ki minus 1, parentheses there. So I think that closes it correctly. So once that's equal to 0, we'll have found the correct v over f. So I'm going to save this. No syntax errors. That's a good sign. This, I don't know why it's telling me this equal sign. It's giving me an underline there, but that should be good. So the next thing we're going to do is we're going to put it through the root solver. So we're going to do root of Rachford-Rice. And then the next thing we're going to do is supply our initial variable. I have to put this in an array, don't I? Because we need to return an array. So I'll just array you. I don't think I need these parentheses actually, because it's contained in an array. So I think man, I think that's correct. So Rachford-Rice, I only caught that because I need to provide an initial guess in the array. So v over f, we'll go with the ratio of, so we'll go 0.5, say it's half and half. And then I don't think there's really anything else we need to specify here, because I don't want to hit 0 in my numpad. And then I want to say dot x and the first item in the list, so it should give us function changed size between cells. That's not good. Vector expected expression. I'm trying to here. Let me check over again. I have the blackboard, an image of the blackboard pulled up right here. Zi, yeah, that's correct, divided by, it's the sum of everything. The Zi is being divided each time. Okay, that makes a lot more sense. So Zi over, wrap this whole thing in parentheses again. There we go. I was about to say, I was like, so the way we had it written before, Zi was a constant being divided by an array, which doesn't really make sense. You can do an array divided by a constant because you'll just divide each item in the array by the constant according to NP rules. But yeah, you can't divide a constant by an array because it would have to output an array. But since you're starting, it just doesn't make sense. So thank goodness we fixed that. And our final answer is 2.48. That's kind of underwhelming. All that work just to get a 2.48 plopped out. But it's no matter because this is our answer. This is the vapor to fluid equilibrium, or the ratio between the two, for which our thing becomes true. So what we want to find out, using this V over F, is to figure out the amount of vapor and the amount of liquid coming out of our flash drum, because we know the amount of stuff going in the feed is 10 moles per second. So we want to know the amounts of vapor and liquid, and we also want to know the composition of the vapor and liquid. So how can we figure that out? Well, now that we have here, I'll set this to V over F is equal to the root. So clear U, run this again. So now we have that, that value saved. Well, since this is V divided by F, if we want to know the volume of vapor, V will just be equal to V over F times F, obviously. That one's pretty easy. And then once we know our vapor, since we already know our feed, liquid's just the difference between the two of them. So the liquid is going to be equal to feed minus vapor. Again, overall very simple. Now that I think about it, a ratio of 2. Question is, vapor is liquid is. Vapor is feed. Huh. Vapor is V divided by F, and V is greater than 2. I should say that's enough somewhere. I can't think of it anywhere. Let's check what V is. Yeah, okay, so we don't have 3 moles of vapor instead of 10 moles of combined liquid vapor. That doesn't make sense. Yeah, that's negative 14. So that's definitively wrong. What the heck did I do wrong here? You can have negative liquid. It doesn't make any sense. Well, that's very curious. You can have Zi divided by, and then this addition is U over F plus 1 over Ki minus 1. Right? Ki minus 1 is the thing divided by 1 here, and then that's the division. And then so that's equals 0. Maybe provide that guess. Actually, it's not that guess though. And this thing should definitely between 0 and 1. Because either vapor is none of the feed, or vapor is all of the feed. There's no way it should be greater than 1. It literally does not make any sense. None whatsoever. I literally talked about this in my video. I'm sitting here staring into space thinking, it's because we're at a point that is way above equilibrium, because Rachford-Rice checks for equilibrium. So if you have more than 100% vapor, that's just saying you're this much far above the point at which everything will have been converted to vapor. So it's just telling us that yeah, we're definitely like past the equilibrium. We are absolutely in vapor territory here. I was like, I'm checking on my map, and there's 2 lines, so it can't be something I'm doing wrong here because I checked my equation and it's correct. I was just didn't seem right, but it's saying that it's more than the feed, basically, which is not literally more vapor than the feed. It's just saying that it is above the point at which the equilibrium exists. There's no longer an equilibrium, so it just becomes about how much can you bubble off before it just is pulled out by the system constantly flowing, essentially. So anyway, now that we've got that kind of hiccup sorted out, and by hiccup I mean major confusion that I had already addressed in my chalkboard video discussing what happens when the V over F goes one way or the other. Anyway, so now that we have the volume of the vapor and the liquid, how do we figure out their concentrations, the way they're composed? Well, again, from our chalkboard video, I'll pull it up again, just in case. We can see that xi is equal to zi over v over f times ki minus 1 plus 1. Right? That's kind of half of the Rachford-Rice equation is that substitution right there. And since we now know v over f, and we knew zi and ki from the beginning, we can just solve for ki as being equal to zi divided by, parentheses, v over f times, space, times, sees ki minus 1 plus 1. So that all contains the vi, that should be correct. And then yi, obviously, since we know that ki is defined as yi over xi, y is equal to, or yi over xi is equal to k, y is defined as f, yeah, what am I saying? Ki times xi, right? Because yi over xi, the slope, if you will, is equal to ki. So we just multiply ki by both sides, all of this, and that should be good. So now we want the actual answers. So we're just going to say, what would be a nicer way to, we can do a print statement. Say, print v l xi. Actually, we'll do them next to each other. V and yi, and then L and xi. And there we go. So these are our numbers. So we have 24 moles of vapor per second, which is greater than the 10 moles of feed per second, which is just saying that we're far beyond the point of equilibrium. And this is the part that actually kind of matters. We have a concentration of 0.229, so basically about 0.23 moles benzene and 0.77 moles of toluene. So our vapor is mostly toluene. And our liquid is negative 14 moles per second compared to the 10 moles of feed per second. And the composition there is 0.11 moles of benzene and 0.884 moles of toluene. These numbers, again, are a bit funky and they're a bit hard to understand because the numbers are so strange, 24 and negative 14 out of 10 feed moles per second. But if we were to try this again and run, KI's, or not KI, but a ZI that by changing that and putting it somewhere within here, because 150 at 393 is, well, it's about here, right? So it would need to be about 0.13-ish. So 0.13-ish of x1. So just out of curiosity, we'll do 0.14, 0.96. Everything again. And we get a final answer that's, here we go, this is a real answer. See, here, look at these numbers. Just by using the graphs we made previously, we can eyeball it and say, we're looking at a, lock temperature 293, 150 pascals. This 0.12 is about 150, so he scooted a bit over until we get to 0.14. will be within the envelope of having both of them at the same time. And you can see right here that we'll have 1 mole of vapor per second and about 9 moles of vapor of liquid per second. And then you can see here the actual compositions, and they actually make sense. Again, toluene is significantly heavily favored, which seems strange until you again realize that there is there's a significant increase in the amount of toluene in the system compared to the feed, because again it's 0.14 against 0.96. I just realized that this doesn't add up to 100%, however, so I should rerun these. And there we go. So now we have real answers, because 0.14 and 0.86 do add up to 100. Bit of an oopsie there. But again, here are our real numbers that fall within the phase envelope. Again, you can tell because these two numbers add up to 10 and neither one is negative. But so here are our real feed. But again, because the question was about 0.4 and 0.6, we'll run everything again. And these are the answers that we're looking for this class investigation. So, since we know all the compositions of the vapor and the liquid flows, and obviously we know their volumes, although they're a bit nonsensical because we're lying outside of the equilibrium state, that's what we were asked to solve for, and since I provided my own true practical example, I feel very completed and happy. So, with this, we're going to wrap this video up. Thank you for watching again, and I wish you all the best evening ever. Good night.